Let's have a look at this question here. So here we have to find out standard change in the Gibbs free energy, right? Delta G naught, that is the change in Gibbs free energy at equilibrium for the reaction, and we have been given reaction of H2O molecule, H2O water in equilibrium with H plus and OH minus ions at 25 degrees Celsius. And we have been given value of log of 55.6 as 1.74. Okay, so pretty straightforward question if you know the formula of change in Gibbs free energy at equilibrium, right? Which is what? Delta G naught. So delta G naught is equal to minus 2.303 RT log K, right? So minus 2.303 into R is the universal gas constant, 8.314, since we are calculating the energy in joules. Temperature given to us is 25 degrees Celsius. So 25 degrees Celsius plus 273 comes out to be 298 Kelvin into log K, right? What is K here? K is the equilibrium constant. And which equation is given to us? That is H2O is in equilibrium with H plus ions and OH minus ions, right? So if we want to calculate the value of equilibrium constant for this reaction, it will be given by the product of the concentration of the products raised to the power their stoichiometric coefficients. So here it will be the concentration of H plus ions into concentration of OH minus ions, right? Raised to the power 1, divided by the product of the concentrations of the reactants raised to the power their stoichiometric coefficients. So this will be concentration of H2O, right, at the raised to the power 1, because the coefficient is 1, and this is at 25 degrees Celsius, right? So what do we know here? We know that the concentration of H plus ions into concentration of OH minus ions is what is given by ionic product of water, right? And we need to have it at 25 degrees Celsius divided by concentration of H2O, concentration of water. What is concentration of water, right? We write it as 55.6 molar, right? This will give you the value of K, which is what? K is equal to 10 to the minus 14, right? So that is the ionic product of water at 25 degrees Celsius divided by 55.6. Correct. So now we have the value of K as well, right? So simply we'll put the value of K and we'll get the value of change in Gibbs free energy, standard change in Gibbs free energy. Okay, so let's put the values now. It will equal to minus 2.303 into R, that is 8.314, into T, that is 298 Kelvin, into log of 10 to the power minus 14 divided by 55.6. Okay. So what do we have here? So we'll approximate a little bit to make our calculations easier. Otherwise, this will be a very, very long calculation, right? So you'll have to approximate. So let's approximate 2.303 as minus 2.3 into 8.314 as 8. Let's approximate 298 as 300, right? Into log of 10 to the minus 14. We are not approximating it, we are simplifying it, right? So there's a property of log. Log A by B is equal to what? Log A minus log B. So this will become log of 10 to the power minus 14 minus log of 55.6. Okay, so minus 2.3 into 8 into 300 into log of 10 to the power minus 14. This is easy, right? Minus 14 will come to the front of the log. This becomes log 10, and log 10 is 1, right? Minus log 55.6, and we have been given that value in the question, 1.74. So minus 1.74. So this comes out to be minus 2.3 into 8 into 300 into minus 14, right? Log 10 is 1, minus 1.74. So minus 2.3 into 8 into 300 into minus 15.74. Let's approximate this as well. So this becomes minus 16, right? And minus into minus is plus, so it cancels out. Now we just have to calculate this multiplication and we'll get our answer. Okay, so we have two zeros here. Okay, so 8 3s are 24. 24 into 16. Let's find this first out. 2, 4, 6 2s are 12, 144, 24. This comes 4, 8, 384. 384 into 2.3. Okay, so let's also have 110 in the 10 in the denominator as well. Okay, so 384 into 23. Okay, 3 4s are 12, 3 8s are 24, 25, 3 3s are 9, 11. 2 4s are 8, 2 6s are 16, sorry, 2 8s are 16, 1, 2 3s are 6, 7 comes out to be what? Just trying to segregate the calculation from the question. Okay, so this comes out to be 2, 3, 1, 6, 1, 7, 8, 8. So this is 8, 8, 3, 2 into 100 divided by 10. So this cancels out, right? So what do we have here? We have 88320 joules of energy. Let's see which option does it match. Okay, so this was an approximate value, right? And this is a positive value. That's what we have to take care, because in the options we are given positive as well as negative values, and they are in kilojoules. Okay, so this comes out to be what? This comes out to be approximately 88.32 kilojoules. So which option is it close to? Well, it's close to option C, which is our correct option. So here we are given this anti-cancer compound, a very big, a very complex compound, right? We have to find out the number of carbon atoms which are sp3 hybridized, right? This compound seems complex and actually too big as well, but the question is not. The question is very, very easy. Okay, so we have to find out the hybridization of the carbon atoms. And how do we find that out? We find it through the steric number. So steric number is equal to what? It is equal to the sum of the sigma bonds that that particular atom is making with other atoms, and the sum of sigma bonds and the lone pairs, right? The sigma bond that atom is making with other bonds, and the number of lone pairs that are on that particular atom, right? So we see here we don't have any lone pairs on the carbon atoms, for which we need to find out the hybridization. So for this particular question, we can say here that there's no lone pair on any of the carbon atom. So for this question, we only have to figure out what? We have to figure out the number of sigma bonds that all carbon atoms are making, right? And that will give us our steric number, and through that we'll know our hybridization. So we know that if we have steric number 4, that means that the hybridization is sp3. If we have steric number 3, the hybridization is sp2, and if the steric number is 2, we have hybridization as sp. Okay, so let's go about these carbon atoms one after the other. So this is our first carbon atom, right? It has what? It has 2 sigma bonds here and 2 another sigma bonds that it is making with 2 hydrogen atoms. So it has what? It has a total of 4 sigma bonds. That means its steric number is 4. That's why the hybridization is sp3. So this is our first carbon atom which has sp3 hybridization, or which is sp3 hybridized. Okay, let's move on to the next carbon atom. So this is the next carbon atom we have. So here we have 1 sigma bond here, 1 sigma bond here, 1 sigma bond here. So this double bond now has 1 sigma bond and 1 pi bond, right? So in total, this carbon has what? It has 3 sigma bonds. That means its steric number is sp2. Sorry, It has 3 sigma bonds. That means its steric number is 3 and its hybridization is sp2. So this is not our carbon. Okay, let's move on to the next. Next carbon, if we see, is also the same. It's making what? It's making 3 sigma bonds, correct? So wherever you see that, a valency of carbon is less, through the bond line structure, that valency is filled by hydrogen atoms, because we don't show CH bonds in the bond line structure, right? So for this carbon atom, we see there are 3 sigma bonds, 1 pi bond, right? Because it has 1 double bond. So 1 double bond will have 1 sigma bond, 1 pi bond. So its hybridization is sp2. So not our carbon. Okay, next we will move on to this carbon atom. This also has 1, 2, 3 sigma bonds and 1 pi bond, because 1 double bond has 1 pi bond, 1 sigma bond. Okay, so this carbon is also what? sp2 hybridized. Let's move on to the next carbon. So next carbon has 1, 2, 3 sigma bond, and there is one more bond which it is making with H, right? So it has what? It has 4 sigma bonds. Steric number is 4. Hybridization is what? sp3. So this is our second carbon atom which has sp3 hybridization, or which is sp3 hybridized. Okay, let's move on to the next. So this also has what? 3 sigma bonds here. 1 sigma bond is also making with hydrogen. So even this is sp3 hybridized. Let's move on to the next carbon atom. So this next carbon atom is making 2 bonds here. Other 2 bonds are the 2 sigma bonds with hydrogen atom. So even this carbon atom is making 4 sigma bonds. That's why sp3 hybridized. Okay, let's move on. Let's move on to the next carbon. We have 1 carbon here. Okay, so this is 1 sigma bond, another sigma bond. Now we have a double bond O. In that case also, we'll have 1 sigma bond and 1 will be the pi bond, correct? So here we can see we have 3 sigma bonds. So it's not sp3 hybridized. Okay, let's move on to the next. Next carbon has 1, 2, 3 sigma bonds and 1 more bond that it is making with the hydrogen atom. So this is our 5th carbon atom which is sp3 hybridized. Next carbon atom here, 1 sigma bond, 2 sigma bond, 3 sigma bond, and it is also making 1 sigma bond with hydrogen atom. So this is our 6th carbon atom which is sp3 hybridized. Let's have a look at this carbon atom. It's the same case. We have 3 sigma bonds and 1 double bond. Double bond means 1 sigma and 1 pi. So that means this carbon it has 3 sigma bonds, right? It's making 3 sigma bonds. That's why sp2 hybridized. Next carbon atom, same case again. It's making 3 sigma bonds. One of the sigma bond is with hydrogen atom. It's making a double bond. That's why one of those 4 bonds is a pi bond and not a single bond. That's why it is sp2 hybridized. Next carbon atom, same case here as well. 1 sigma bond, 2 sigma bond, 3 sigma bond, and the double bond is what? Double bond involves 1 sigma bond and 1 pi bond. That's why the steric number of this carbon atom is sp2. The steric number of this carbon atom is 3. That's why it is sp2 hybridized. Okay, let's have a look at other carbon atoms that are left. So this carbon atom, if you see all these 6 carbon atoms, right, in this benzene ring, these all are sp2 hybridized because they all are making double bonds with each other, right? You can see here. So they all have, not all, but we can see that these 2 carbon atoms are making sigma bonds with H, right? However, we can see that all these 6 bonds, they are making 3 sigma bonds and 1 pi bond, right? So that's why all these 6 carbon atoms are sp2 hybridized. Okay, let's have a look at the next carbon atom. which is the next carbon atom? Are we done with all the carbon atoms? We are actually not. This methyl group, right? It also has a carbon atom. So this is what? This is CH3O, right? All these methyl atoms are actually OCH3. So this is OCH3. This is also OCH3. This is also OCH3, right? It's bonded to the carbon in the benzene ring with oxygen. Okay, so here looking at these carbon atoms, what can we say about these carbon atoms? Well, we have C, we have H, and O, right? So it is making what? It's making 4 sigma bonds. Steric number is 4. Hybridization is sp3. So this is our what? This is our 7th carbon atom, which is sp3 hybridized. Similarly, the other 2 are exactly the same. So even this carbon atom is sp3 hybridized. Here I would mention this carbon atom. So I've written in bracket, like OMe is same as OCH3, right? Me is what? Me is methyl group. Okay. And this is the 9th carbon atom, which is sp3 hybridized. So how many total, sp3 hybridized carbon atoms do we have here? We have 9 carbon atoms. Let's check out the options. Well, it matches with our option C, which is the correct option. Let's have a look at this question here. So here we are given 3 aqueous solutions, right? One is what? One is of NaOH, which is a base. One is of HCl, which is an acid. And one is of H2SO4, which is also an acid. So what we are doing, we are mixing these aqueous solutions together. And we have to find the nature of the resulting solution. If the resulting solution would be acidic, or it would be alkaline, or it would be neutral. Right. So how do we proceed from here? Well, the first thing is you have to find out the milli equivalents of all these aqueous solutions that are given to you. And we'll see that after reaction, milli equivalents of which of the aqueous solution is left, and that will give us the answer. That will tell us the nature of the resultant solution. Okay, so the first thing that we have is NaOH, which is 100 ml at 0.5 normal. So milli equivalents of NaOH will be 100 volume, right? So we are finding milli equivalents, that's why the volume will be in milliliters. So 100 into 0.5, that is 50 milli equivalents, right? So the milli equivalents of NaOH is 50, okay? Next we have 1 by 5 or n by 5 HCl, okay? So milli equivalents of HCl, that will be 100 milliliters, because that's the volume for all these 3 solutions, into 1 by 5. That is 20 milliequivalents. What about H2SO4? That is 1 by 10. Okay. Milliequivalents of H2SO4. That is 1 by 10 into 100, right? I can write it as 100 into 10 as well. It's the same thing. 100 is the volume. 1 by 10 is what? Normality. What do we get? We get 10 milliequivalents of H2SO4. So if we see here, the milliequivalents of base, right? If I say OH minus is what? 50. And milliequivalents of H plus, that is what? That is this 20 plus 10. That is 30. Correct. So when the reaction happens, what would happen? So OH minus ions will react with H plus ions to give water, right? So if we look at this data in front of us here, we can see that 30 milliequivalents of acid will neutralize 30 milliequivalents of base, but we will still be left with some milliequivalents of base, right? How many milliequivalents of base would we be left with? That will be, total we have 50, right? Out of 50, 30 will react with acids. So we'll be left with 20 milliequivalents of the base in that resultant solution, right? So what does it leave us at? Well, it means that the base would be left in the aqueous solution. That will turn the resultant solution alkaline. The pH will be above 7. So which one is the correct option here? Well, it is option C. let's have a look at this question. So here in this question, we are converting 2,3-dibromobutane to 2-butene with zinc dust, right? And we have to find out which process is this. First, let's have a look at the reaction. So we have 2,3-dibromobutane. So we have 4 carbon atoms, and at second and third carbon atom, we have bromine atoms. So in the presence of zinc dust and heating it, what do we get? We get but2ene, right? So first find out the easiest way to do this, like the way through which it will take you very less time, then we'll go into much more explanation. So here we can see that what is happening. We have CH3 here, this is CH, H, and here it is also CH3. Okay. So if we just look at the reaction, just looking at the reaction, what do we know? We are removing these 2 bromine atoms. That's what is happening, right? So we have 2 bromine atoms on the reactant side in the molecule. However, in the product side, we do not have these 2 bromine atoms. We have a double bond between those 2 carbon atoms on which these 2 bromine atoms were there, right? So what is happening? We are removing the halogen, which is bromine here, right? So if we look at the options here, we can see, so this is dehydrogenation. Dehydrogenation means removal of hydrogen. Obviously, we are not removing hydrogen. Next is dehydrohalogenation. So that means we are removing hydrogen and halogen atom also, right? No, we are not. We are just removing halogen. So even B is not correct. What about C? C is dehalogenation reaction. Yes, we are only removing the halogen atoms. So yes, option C is correct. Option D is denaturation, which is not related to here. So option D is not correct, right? Okay. So denaturation is in the bio. It's not in the chemistry. Okay. So dehalogenation. So we have come to our answer, right? But let's look at the reaction in a little bit detail. So we have 2 bromine atoms attached to 2 carbon atoms which are adjacent to each other, right? So what happens in the presence of zinc dust, and when you heat it, these bromine atoms, they are removed, and you get what? You get double bond between the 2 carbon atoms. Remember that this type of halogen, so this type of halide, this is called vicinal halide, in which the halogen atoms are attached to carbon atoms which are adjacent to each other, right? So this reaction is a typical reaction for vicinal dihalides. So if you heat vicinal dihalides in the presence of zinc dust, what happens? Dehalogenation takes place. These bromine atoms or these halogen atoms get removed, and what do you get? You get alkene. So this is an important reaction for the preparation of alkene, right? And we have already found out the correct option to this question is option C. So we have a reaction in front of us in which alkyl halide is our reactant, right? And alcoholic KOH is the reagent, and we are getting 2 alkenes as a product. And we have to find out which is the major product out of these 2 alkenes. Okay, so let's have a look at the reaction first. So we have an alkyl halide, CH2, CH3, and Br on carbon 2, right? So in the presence of alcoholic KOH, what happens? Well, this is the reaction for the preparation of alkenes, and this undergoes dehydrohalogenation. What do we mean by dehydrohalogenation? D means removal. And what are we removing? We are removing hydrogen and halogen, that is HX, which is bromine in our case here, in our reaction here, right? So X, or I would say the halogen atom, that we know what we are removing. But what about the hydrogen atom? Well, the hydrogen atom that is removed in this reaction is the beta hydrogen. Now, what is beta hydrogen? Well, the carbon on which the bromine atom or the halogen atom is attached is called the alpha carbon. right? And the carbons that are attached to this alpha carbons are called the beta carbons, right? So we have 3 beta carbons here, and the hydrogens that are attached to these beta carbons are beta hydrogens, right? So we have to remove beta hydrogen. If you look at this carbon number, this carbon and this carbon, right? You'll see both of them are identical. And their environment is exactly the same, right? So these 6 hydrogens are same type of beta hydrogen. So if you closely look at this molecule, at this alkyl halide here, you'll see that you have 2 types of beta hydrogen. One is this type. These 6 atoms combine, give these 6 atoms combine and give one type of beta hydrogen, and these 2 hydrogens, these are another type of beta hydrogens, right? So that's why it leads to what? It leads to 2 types of products. Let's see. So if we remove, let me clean up here. Yeah. So if we have alpha carbon, this one is the alpha carbon, and if we remove, let's say, this beta hydrogen, right? So what would we get? We'll get CH2 double bond C, CH3, CH2, CH3, right? However, if we remove the other beta hydrogen, we have 2 types, so we are removing the other beta hydrogen now, right? Along with bromine atom. So bromine is all obviously we are removing, right? This is minus HX. We are removing both hydrogen atom and halogen atom. Okay, so if we remove the other beta hydrogen along with the halogen atom, what do we get? We get CH3, C, CH3, double bond CH, CH3. Correct. So these are the 2 alkenes that are given to us in the question as well. We have to find out which out of these 2 alkenes, which one is the major product. How do we find out the major product? Well, the most stable product is usually the most, major product, right? So let's compare the stability of these 2 alkenes. And how do we do that? Well, for the stability of alkenes, it's pretty clear. So if the number of carbon atoms is same, we have what? We have total of 5 carbon atoms in both the alkenes, right? So we can compare them on the basis of number of alpha hydrogens. Now we should know how to calculate number of alpha hydrogens in an alkene. Let's see how do we calculate that. So this C, let me rewrite it so that it becomes better for you to understand, right? Okay. So this entity, C double bond C, is counted as one entity, right? So the hydrogens that are present to the carbon atoms which are attached to this entity are the alpha hydrogens. Okay. So let's see how many alpha hydrogens does this first alkene has. Okay. So this is the first carbon that is attached to this entity, and it has 3 hydrogen atoms. And this is the second carbon that is attached to this entity, and it has 2 hydrogen atoms. So total alpha hydrogens is 5 for the first alkene, right? Here, if you see on the left side, the entity, the hydrogen atoms are attached to the entity. So we don't count this, okay? Now let's have a look at the second alkene. Okay. So here, what do we have? We have our entity here, C double bond C, right? Let's see how many alpha hydrogens does this alkene have. So this carbon has what? 3 hydrogens. One more carbon atom which is attached to this entity. It also has 3 hydrogen atoms. There is one more carbon that is attached to this entity which has 3 hydrogen atoms, right? So this gives what? This gives total of 9 hydrogen atoms. So I would say 9 alpha hydrogens. So more the number of alpha hydrogens, more will be the stability, right? That's how we decide the stability of the alkenes which have which have equal number of carbon atoms. Okay, so let's see which alkene is the major one. Well, this is the alkene which has what? Which has 9 alpha hydrogens, and this is the alkene which has 5 alpha hydrogens. So we know that the first product, the one product, is our major product in this reaction. Let's have a look at the options. So we know that they are not going to be formed in equal amount. Second option, second product is also not the major product, right? None of these is not correct. So which one is the correct? Well, we know that the first product will be formed as a major product, and the correct option to this question is option A.